Okay, in this video, we're going to be doing 3 different integrals that involve the greatest integer function. The source for these integrals is the JEE Mains exam, and it's got a lot of hard problems on it. So let's take a look at them and see if we can do them. I would say when you go into a problem like this, if you've never seen it before, if you've never done anything like this, if you're in like Calc AB or Calc BC, for example, they seem almost impossible to begin with, but then you get used to them and they're not that bad. But you got to look at them to really get acquainted with it. So let's do it. So our first one is we're going from 0 to 2, absolute value of 2x squared minus 3x, which is kind of like an entirely different skill that we're testing here, but plus the greatest integer of x minus 1/2 dx. All right, so I'm going to basically break this into 2 different integrals and do each of them and then add up the values, right? So this is our first integral, and then this will be our second. So we're going to deal with the absolute value first. So that's the integral from 0 to 2, absolute value of 2x squared minus 3x dx. When you're dealing with this, you kind of hope that it's just linear and you can do it geometrically, but this one you can't. So instead I'm going to rewrite the absolute value as a piecewise function. So let's factor the thing that's inside there. So we got an x and a 2x minus 3, and we'll set that equal to 0. So that gives us 0 and then 3/2. Now we need to figure out where the 2x squared minus 3x is positive and where the 2x squared minus 3x is negative, so we can rewrite as a piecewise. So I'm just going to do a sign chart for it. So 0, 3/2. It's a quadratic that opens up, so plus minus plus. Okay, we're actually only interested from 0 to 2, so that part below 0 doesn't really matter. From 0 to 3/2, the function is negative, so the absolute value is the opposite of that. So we're going to have the opposite of 2x squared minus 3x. That's from 0 to 3/2. In this case, because we're going to integrate, you kind of like want to include 3/2 both times, but it's fine. It doesn't really matter. From 3/2 to 2, which is, again, the only part we really care about, the quadratic thing is positive, so we just get 2x squared minus 3x. Okay, so now we've written this piecewise, so we can take our original integral that I've labeled number 1, and we can rewrite this as 2 separate integrals. So that's going to look like, so 0 to 3/2 of the opposite of 2x squared minus 3x, or 3x minus 2x squared, plus the integral from 3/2 to 2 of 2x squared minus 3x. And there's like nothing nice that happens here. You just have to do both of them. There's no like symmetry that you can use to cancel or anything like that. So we'll do this one. It's just reverse the power rule, and then use the fundamental theorem on it. So 3/2 x squared minus 2/3 x cubed from 0 to 3/2. So really the hardest part of this is rewriting the absolute value. And then once you're done with that, it becomes kind of a standard integral. So here we'll get 2/3 x cubed minus 3/2 x squared, and that's from 3/2 to 2. Now we apply the fundamental theorem, so we plug in 3/2, and we end up with 27/8 minus 9/4. When you plug in 0, you just get 0. Plus, when we plug in 2, we get 16/3 minus 6 minus 9/4 minus 27/8. And you can pause and check that, or maybe hopefully you're just working ahead and then just looking to see if it worked out. We can combine some stuff here. We end up with 54/8 minus 9/2 minus 2/3. And then, I don't know, you can simplify that. You end up with 19/12. But remember, that is not the answer to the problem. That's the answer to the first integral that we came up with. We still have to do the part where we integrate the absolute, not the absolute value, the greatest integer function. So let's move on to part 2 of this integral. So we're going 0 to 2, greatest integer of x minus 1/2 dx. I personally think the easiest way to deal with this one is just to remember what the greatest integer function looks like. So greatest integer function, we got, looks kind of, I mean, it looks exactly like this, right? So it's the integer less than or equal to, the greatest integer less than or equal to the value. So like the greatest integer of 1.5 is 1, because that's the integer that is the greatest integer less than that. I think of it as the integer to the left on the number line. So 1.5, what integer is to the left? 1. I don't know, like 0.6, what integer is to the left? 0. Negative 0.1, what's to the left? And negative 1, right? So it's the integer to the left. So now I need to take this graph and just shift it 1/2 unit to the right. So This is a little transformation problem. So we still have, the same general setup, but we're shifting it 1/2 unit to the right. So it'll look now like this. And I think that this is the best way to do this. So we actually now can take our integral from 0 to 2 of the greatest integer of x minus 1/2 and break it into 3 separate integrals. We're going to go from 0 to 1/2, 1/2 to 3/2, and then 3/2 to 2. So let's start doing that. So 0 to 1/2, the thing is -1, and then 1/2 to 3/2, the thing is 0, and then 3/2 to 2, the thing is +1. Okay, so we don't actually have to do anything on this, in my opinion, because obviously the middle one, 1/2 to 3/2 of 0, is just going to give us 0. But then if you look, you're only going 1/2 unit on the x-axis from 0 to 1/2, and it's -1, so that'll just give you -1/2. Then you're going from 3/2 to 2, which is 1/2 unit on the x-axis, +1, which gives you +1/2. So you just get -1/2 plus 1/2. So those cancel. We just get 0 for that, which means that we've answered the question. We went from 0 to 2 of the absolute value of 2x squared minus 3x plus the greatest integer of x minus 1/2 dx, and we got 19 over 12. So it's almost like the greatest integer there is just, and maybe we should have known by symmetry. I mean, certainly after we graphed the greatest integer of x minus 1/2, I still think it's good to go through it, but you want to be on the lookout for stuff like that. So there was some symmetry there where we could have taken advantage of it and just known that it was 0 right away. Okay, that's one integral. These are kind of in ascending order of difficulty. So the next one, I think, is a little more difficult than the one we just did. And then the final one, I think, is potentially much more difficult, but not actually, just like it has more steps. Let's take a look at the second one. We're going -3 to 101, which right away, that's like a weird interval to use. Greatest integer of sine of pi x plus e to the greatest integer of cosine of 2 pi x dx. So we have 2 trig functions involved, and they have different periods. And I am just going to break this into 2 again. I think it's like the way to go. I'm going to deal with the first part, deal with the second part, take their answers, add them together, right? So we got to deal with basically sine of pi x. We got to figure out what's going on with sine of pi x, and then we will take the greatest integer of whatever we see happening. So the period of this is 2 pi over pi, so the period is just 2. And let's make a graph, because I think the graph can really help us out. So 2, 1, split in half. Let's graph sine. We got this. Okay. Now we need to figure out what the greatest integer less than or equal to. So if you look between 0 and 1 on the x-axis, the values of sine are always between 0 and 1, and the greatest integer less than or equal to anything between 0 and 1. I mean, there is like at 1, you get exactly 1. But that's not going to impact it, because if you integrate from, at 1/2, you get exactly 1, right? So if you integrate from 1/2 to 1/2, you just get 0. So it's not really impacting anything. So I'm pretty comfortable just saying that our greatest integer of sine of pi x is going to look like basically 0. And then from 1 to 2, you're always getting a number from like 0 to -1, and the greatest integer less than or equal to that is going to be -1. So there is no caveat there, like, because -1 is the greatest integer less than or equal to -1. So, if you worry about it, you can end up creating like a lot of scenarios, but I think we're okay. At 1/2, there is a problem, so it depends on how rigorous you're trying to be. But I think it's okay because we're just going to integrate that and get 0 anyway. All right. So we're always at 0 from 0 to 1. We're always at -1 from 1 to 2. Now, the question is, how many periods are we dealing with? Because this question really is a question of whatever happens on one period of a trig function happens on every period of a trig function. So if I can figure out the answer for one period, I can just multiply it by the number of periods that are involved. So how many periods are involved here? Well, we're going from -3 to 101. So the question's actually nice in that it gave us an integer number of periods, right? So -3 to 101, all we have to do is 101 minus -3, sorry, and then divide that by the period, which is 2. We get 52. So we have 52 full periods. So what we should be able to do is say that our integral that we're doing, the first one here, is going to be 52 times whatever happens between 0 and 2. And between 0 and 2, we're doing 0 to 1 of 0 plus 1 to 2 of negative 1. So integrating 0 gives you 0. From 1 to 2 of negative 1 just gives you negative 1, so this gives us negative 52. That's the first part of the integral. So now we just have to do the second part, and it's going to be really similar, which is what I mean by, like, do the problems. Whenever you're preparing for a big exam, the best thing you can do is find problems from that exam and just do them, in my opinion. So the second integral, let me go back for a second, is going to be from negative 3 to 101, e to the greatest integer of cosine of 2 pi x. So that's what we're doing. So cosine of 2 pi x is important, and we want to figure out what's going on there. So the period is 2 pi over 2 pi. The period is 1 this time. So if we had 52 periods last time, we're going to have 104 this time. I mean, I'm going to go through and do the work anyway, but like think that way. Let's look at a graph, because that is, the easiest way to deal with a trig function is to create a graph of it. So we have this, and it's just a normal cosine graph. So here we go. Same logic, right? Like, I know that you do actually get 1, but I'm going to just fill in between 0 and 1/4. We're doing the greatest integer of cosine of 2 pi x. Between 0 and 1/4, every value that you get is going to be, I know at 0 you get 1, but I'm not worried about that. Every value you get is between 0 and 1. The greatest integer less than that is 0. And then 1/4 to 3/4, the greatest integer less than or equal to will be negative 1. And then 3/4 to 1, the greatest integer less than or equal to it will be, again, 0. Okay. So we said we need to know how many periods we're dealing with. And so, again, I'm going to run through it, but we already know the answer, kind of. So we're going from negative 3 to 101, which means we can do 101 minus negative 3 and then divided by 1. But that's just 104. There's 104 periods. So whatever happens on one period is going to happen on each of those periods. So we just need to figure out what's happening for one period. So what I'm going to do is I'm going to say it's 104 times what's happening on one period. So 0 to 1/4, we're going to have e to the 0, plus 1/4 to 3/4, we're going to have e to the negative first, and then 3/4 to 1, we'll have e to the 0. So don't forget that it's not just the greatest integer of cosine of 2 pi x, it's e to the greatest integer of cosine of 2 pi x. And that's really important. I imagine that a lot of people probably just forget that because it's a complicated problem. All right, let's integrate each of these. So the first one, e to the 0 is 1, so you just get 1/4 minus 0, and then times 1, so you just get 1/4. And then for the next one, you get e to the negative first, basically times x, and then you have 3/4 minus 1/4, which is 2/4 or 1/2, so we get 1/2 e to the negative first. And then for the last one is basically the same as the first part, really. So we're going from 3/4 to 1 of 1, so that's just going to be 1/4. All right, and we can clean this up, obviously, I guess. I don't know if it's obvious, but I think it is. We get 1/2 plus 1/2 e to the negative first, which is 52 plus 52 e to the negative first. And then we're basically done, but we have to take this answer that we just got and add it to our previous answer, so that overall our final thing, negative 3 to 101, of the greatest integer of sine of pi x plus e to the greatest integer of cosine of 2 pi x, it's going to be negative 52 from the first part of the integral, plus 52 e to the negative first, so final answer, 52 over e. Okay, so that's a second problem. The third problem that I found, I think is a little more difficult, just because it's a little more involved, but it's the same exact process. And as I said, like, the more you do them, the more you get used to it, so that you're not afraid of a greatest integer function. So we're going 0 to 1, greatest integer of 2x minus the absolute value of 3x squared minus 5x plus 2, plus 1, and then like close the greatest integer function, dx. All right, so again, there's an absolute value involved. And again, I think our only option is really going to be to rewrite it as a piecewise function and then go from there. So that's what I'm going to do as a first step. So we're dealing with this. So 3x squared minus 5x plus 2 actually factors, which is great. So it's going to give us, we'll have a 3x, we'll have an x, and then we're going to go minus 2, minus 1. Okay, we're going to do a sign chart for this so that we can figure out where that thing is positive and where that thing is negative so we can properly deal with our absolute value. So we got this. So we got pluses, minus, and pluses. And remember, we're only interested from 0 to 1, so the part to the right of 1 doesn't really do anything for us here. Okay, so the absolute value of 3x squared minus 5x plus 2 is going to be between 0 and 2/3. Since that quadratic is positive, you just take it out of the absolute value. So 3x squared minus 5x plus 2, that's from 0 to 2/3. Remember, the 0 just comes from the problem, right? I mean, really, technically, you're just saying when x is less than 2/3, but for our purposes, 0 to 2/3. And then between 2/3 and 1, the quadratic is negative, so its absolute value is the opposite of the quadratic. So it'll be negative 3x squared plus 5x minus 2. And that's we only care about it from 2/3 to 1. It's also only true from 2/3 to 1, so I didn't really need to specify that, but I did. All right, so what are we doing? We're going to take this integral and we're going to rewrite it by using the piecewise function. So it becomes 0 to 2/3. We got 2x minus the quantity 3x squared minus 5x plus 2, because that's what we replace the absolute value with on that interval, plus 1 dx. And then plus the greatest integer of, 2/3 1, greatest integer of 2x minus the opposite, so negative 3x squared plus 5x minus 2. And we're using the opposite because on that interval, the absolute value, or rather the quadratic is negative, so the absolute value is the opposite of it. So we get this. I'm going to rewrite this one more time so that it's like cleaner. And then there will be two integrals, and we're going to deal with each of them separately. And this is ruthless as we deal with it. So the reason I say that is like there's not going to be a lot of integers involved, if there are any integers involved. But that's okay. The more you look at the problems that are on this particular exam, the more you realize the exam writers don't care about that. They care if you like really, really know your stuff. So I'm going to deal with this first integer first. Greatest integer, negative 3x squared plus 7x minus 1. And we're also integrating it, but like really just dealing with the greatest integer is the issue. So we're only interested in 0 to 2/3. I'm going to name the function. So I'm going to say f of x is the quadratic. And then we're just doing the greatest integer of the quadratic. I think that just makes the notation a little easier as you go through the problem. So first thing I need to do is I need to figure out like, what does this function look like? I mean, it's a quadratic and we can definitely graph a quadratic. I'm going to use a little calculus to figure out if I'm increasing or decreasing. So the derivative of this thing is going to be, and I don't know why I didn't just write f prime there, but I didn't for some reason, is equal to 0, and then that'll give us 7, 6. I'm going to do a little sign chart here. So this is a sign chart for f prime. You go from positive, right? If you plug in negative 1 billion there, you get positive. So you go from positive to negative. And that means that we are only interested between 0 and 2/3 for this particular part. So our function is always increasing. And that's useful because now that I know that it's increasing, I can figure out the values at the endpoints. This would be very challenging if sometimes this was increasing and sometimes decreasing. I'm going to figure out the values at the endpoints. So I'm going to do f of 0, which is definitely negative 1. I'm going to do f of 2/3, which should be negative 4/3 plus 14/3, and then I'm going to say minus 3/3, which gives us 7/3. Okay, so always increasing, you go from negative 1 to 7/3. We need to know which integers are between those two values so that we can apply the greatest integer function. So what I'm going to do, or what I think is useful, is to kind of like fake sketch it. Like this isn't a real graph, but it's close. So we know that 0, negative 1 is there. We know that 2/3, 7/3 is there. Now, between negative 1 and 7/3, we get 0, we get 1, and we get 2. So these are the integers that we need to worry about. What we really need to worry about is what x values give us those integers. So we got a lot of quadratic equations to solve. So let's start doing that. So step 1, f of x is equal to 0. So if f of x is equal to 0, that means negative 3x squared plus 7x minus 1 is equal to 0. quadratic formula comes up everywhere on this exam, it turns out. So it's going to be the opposite of b plus or minus square root of b squared minus 4ac all over 2a. So this is 7/6 plus or minus radical 37, but 7/6 is already bigger than 2/3, so if I add something to it, that's not going to work. So the only one that comes out of this is 7/6 minus radical 37/6, so 7 minus radical 37 over 6. So this is one x value, right? So between x equals 0 and 7 minus root 37 over 6, we're going to greatest integer those. All the y values are between -1 and 0, so the greatest integer of that interval will be -1. That's the logic. All right, now we got to do the next one. F of x equals 1. -3x squared plus 7x minus 1 equals 1. Equals 0, sorry. Why am I saying 1? No, equals 1, yeah. And then I have to move it all to one side. 3x squared minus 7x plus 2 is equal to 0. So we have to use a quadratic formula on this. Oh, no, we don't. This one actually factors. So we'll do 3x, and then we'll do an x, and then we got a -1 and a -2. Okay, so this factored, that's good. So this will give us 1/3, and it'll also give us 2, but 2 is way bigger than 2/3, so we don't really care about that. Our next value is 1/3. So everywhere between 7 minus root 37 over 6 and 1/3, the y values of the function are between 0 and 1, not including 1. Well, I mean, in between, then, yeah, well, like, not including 1. So the greatest integer on that interval will give us 0. 1/3 will get accounted for when we do the next part, so you don't need to worry about that. Also, I'm going to draw another picture to kind of like illustrate that, but keep that in mind, right? So between 0 and 7 minus root 37 over 6, greatest integer will be -1. Between 7 minus root 37 over 6 and 1/3, greatest integer will be 0. And now we need to find the next one, so we got to set this thing equal to 2, which gives us this, moving everything to one side, and again, with the quadratic formula, we get -7 plus or minus root 49 minus 36 over -6. Again, with the logic, 7/6 is already bigger than 2/3, so if I add something, not going to work, so I have to subtract. So we have this. You can also like take it on faith that these x values that we're getting are increasing because we are working with the same quadratic function every time. If that wasn't the case, we'd have to also sit down and think like, what is the relationship between all of these x coordinates that we're getting? But we don't have to deal with that because they're all coming from the same quadratic, so it's not as big a problem. All right, I'm going to take these values, I'm going to redraw the picture on another page and kind of like go through my logic of what's happening. And like, it doesn't feel like it, but we're kind of almost done with this problem. All right, so we had our point at 0, -1. Now we have these other points, and I'm going to fill them in. So it's 7 minus root 37 over 6, 0, 1/3, 1, 7 minus root 1, 3, which is root 13. I don't know why I said it that way, over 6, and then finally 2/3, 7/3. Now what can we do with this? All right, so I'm going to make this chart. And on this, I'm going to put down the greatest integer of f of x. I think I really called this, this one's still f of x. All right, between 0 and 7 minus root 37 over 6, the y values of the function are between -1 and 0, so the greatest integer is going to be -1. You can see I highlighted in a very poor choice of color between -1 and 0 on the y values. And then 7 minus root 37 over 6 to 1/3 is this part, which again, maybe that's a poor choice in color. You're always between 0 and 1, so the greatest integer will give you 0. Then 1/3 to 7 minus root 13 over 6, you're always between 1 and 2, so greatest integer will be 1. And then 7 minus root 13 over 6 to 2/3, you're always between 2 and 7/3, but the greatest integer will just give you 2. That one's a little less clean. All right, now why did we do this? We did this because we need to integrate from 0 to 2/3 the greatest integer of f of x. That was our goal. We can now break this up into 4 separate integrals, right? And they're the integral from 0 to 7 minus root 37 over 6 of the greatest integer is -1, plus from 7 minus root 37 over 6 to 1/3, the greatest integer is 0. That's nice. And then plus 1/3 to 7 minus root 13 over 6, the greatest integer is 1. And then from 7 minus root 13 over 6 to 2/3, the greatest integer is 2. So you just like deal with it, right? Like this is an annoying problem, but it's a problem on the exam. You got to be able to do it. So you just like step in and deal with it. All right, so here, fundamental theorem. Fundamental theorem on this at least is pretty easy. It's all like integrating integers, so you just get -1 times the difference between the bounds, and then you get 0 times the difference between the bounds, which is just 0. And then you get +1, the difference between the bounds, so 7 minus root 13 over 6, minus 1/3. And you're looking at this and you're like, not a lot is going to cancel, and that's true, and we're just going to, again, just deal with it, to the difference between the bounds. So at least you end up only integrating integers, which is nice. You can think of those as rectangles, and you know the base and the height. This we can kind of clean up. I thought the easiest thing to do is just like go through and distribute everything. So that's basically what I did. And then I'll collect the like terms. And as I mentioned like a long time ago, we're almost done with the problem. And if I wasn't having to explain the problem as I went, things would be going a little more quickly for me. But there's a lot of places you can make mistakes here. So cancel those. Root 37 over 6 is not going anywhere. Negative root 13 over 6 and 2 root 13 over 6 are going to cancel to give us just 1 root 13 over 6. And then we got, basically we have -8/3 plus 4/3, so you have -4/3. All right, that's the first part of our integral, because remember, there's a second part. So we've already solved the first part here, and we got whatever we wrote down there. We'll return to it later. We now need to solve the second part, which again is just not like the first part. Like there's no symmetry we can use. I was hoping for that, like, you know, something super clever. I don't see it. So I'm going to do basically the same thing again. So from 2/3 to 1, I'm going to call this thing g of x so that I can then just refer to g of x because I think that'll be easier. So 3x squared minus 3x plus 3. Yeah, so I'm going to find the derivative, see if this thing, like, so worst case scenario would be if the vertex was somewhere between 2/3 and 1 and you had to deal with like increasing and then decreasing and really think. Fortunately, we don't have to do that. G prime is 6x minus 3, which equals 0 at x equals 1/2. We're going to do a sign chart. So 1/2, plug in a negative value and you get a negative, and then plug in a billion, you get a positive. So you go negative to positive, which means, because we only care from 2/3 to 1, that means that this function is always increasing, which is great. We'll just find the values at the endpoints and see what's happening, right? So g of 2/3 is going to be 4/3, and then minus 2 plus 3. So that's 7/3. And then g of 1 is going to be 3 minus 3 plus 3, which is just 3. And something really interesting happens. If we put the points, 7/3 is already bigger than 2, and 3 is definitely just 3. So everywhere between x equals 2/3 and x equals 1, the y values are between 2 and 3. So on this interval, this is better. On this interval, we only ever get a greatest integer of g of x is equal to 2, which is fantastic, which means like our integral is just the integral of 2. Couldn't be better. I mean, geez, think about what we did for that first part. Like, is that a trend? I don't know. I haven't done enough problems to know if like when this happens, you will get like one easy one and one hard one. I would guess that that's not a trend and it's just like happened here. So this will just be 2 times the difference between the bounds. So 2 and then 1 minus 2/3. So 2 times 1/3, which is 2/3. And we're basically done with the problem. So here was what we had. I'm just going to import my answer to the first one, which you may or may not remember. It was root 37 over 6 plus root 13 over 6 minus 4/3. And then plus our answer to the second one was 2/3. And we're just going to get a common denominator and we will be done. And so this is like a survey of interesting problems that you will see involving the greatest integer function. The source for these was the JEE Main, which is a test that I'm starting to enjoy doing practice problems from. I hope this was helpful, and good luck.